So next, let's take a look at these different RAID levels or different RAID configurations that we'll be talking about in this class. So specifically, we're interested in these four different RAID levels, namely RAID-0, RAID-1, RAID-4, and RAID-5. So we're going to skip RAID-2 and RAID-3 because they are kind of less interesting compared to the rest of the more fundamental, more basic ones, okay? So let's first talk about the first level, the baseline case, which is called RAID-0, RAID level 1, RAID level 0, sorry, okay? Which serves as the best case baseline for in terms of both performance and capacity, but it definitely sacrifices on the third metric, the third dimension, which is reliability. Let's zoom in and take a look at why. Okay, so RAID-0 is often called data striping. Okay, by striping, I mean it stripes the data across multiple hard disk drives. Okay, and because it's a baseline, it's the most baseline case, it doesn't support reliability, so there's no redundancy at all. Okay, it doesn't support data redundancy, so the reliability level is literally 0. So given that, for the first two dimensions, for the first two metric, it serves as a uppercase baseline, the best case baseline, okay? The best case in terms of performance and capacity by sacrificing reliability. So it's always a trade-off. If you want to gain the best for the first two dimensions, you get a sacrifice on the third dimension, okay? So at the bottom of the slide, it shows the logical mapping relationship between the logical namespace to the physical hard disk drives. So it basically interleavingly map the logical blocks to one of these two hard disk drives, disk 0 and disk 1. For example, all the logical block number, the even number gets mapped to the first disk, which is disk 0. And all the odd numbers gets mapped to the second disk, which is disk 1. So this is just a simplified case. And in the next couple of slides, we're going to take a look at more realistic examples. So here we're talking about a 4-disk RAID-0, okay? A 4-disk RAID-0, which is a typical configuration for a RAID configuration. So in this case, a stripe means a stripe of data that assemble the same offset of the same block at the same offset across all the 4 disks. In this case, a stripe is, for example, 0, 1, 2, 3, or the second stripe is 4, 5, 6, and 7. It combines all the logical blocks that belongs to all the disks, each and every one of the disks involved in RAID-0. So this is called a stripe. Okay. So the next question is, so given a logical address A, how to calculate the disk that A belongs to, the physical disk that A belongs to, and the offset that A belongs to. By offset, you can think of offset as the ID of the stripe. So it's called stripe ID. Okay, how to calculate that? So you can just simply use these two different operations, binary operations, modulo and dividing. Okay, so the disk ID, how to calculate the disk number is by using modulo. A modulo, the total number of disks. Okay, and how to calculate the stripe ID or the offset within a particular ID, within a particular disk, is by using dividing operation, divide. Okay, so if you take a look at this number, logical block number 2, so it belongs to which disk is 2 modulo 4 gives you 2. So the remainder of this divide operation gives you 2. So it belongs to the third disk. And you use 2 divided by 4 gives you 0. So that means its offset within disk number 2 is 0. So that means it belongs to stripe 0. And we have stripe 1, 2, stripe 3 over here. Okay. Okay. So we have basically 2 logical dimensions. So again, as the next example, if you want to calculate logical address 13, which disk it belongs to and which offset it belongs to, modulo the remainder gives you 1. So that means it belongs to disk number 1, which is the second disk. Since it's located over here, you can just eyeball it. You spot it over here, right? In terms of offset, divided by 4, because we have a total number of 4 disks. So it gives you 3. So that means it belongs to the 4th stripe, okay? Stripe number 3, which is the 4th stripe. Typically, we assume, for simplicity, we assume a chunk size or a chunk granularity of 1. That means each chunk only be stored at one single place, right? So just like the example shown above. But in other cases, the chunk size could be even coarse-grained. In this case, assuming we have a chunk size of 2 instead of 1, it will span like multiple stripes, okay, just like this. So this belongs to a single chunk because we need to look into a single disk level within a single disk if we're talking about a chunk size of 2. And here, assume a chunk size of 2 is 2 disk sectors or 2 disk blocks. It spans 2 disk blocks. In this case, it's 0, 1, and 8 and 9. If you take a look at disk number 2, it's 4 and 5, and 12 and 13. But for simplicity, in all of the following examples, we just simply assume that the chunk size is 1. So that means each RAID chunk only spans one single disk sector. Okay? So next comes with the analysis, the theoretical analysis part. So if theoretical, I mean, in theory, how much it could perform, how best it could perform in terms of performance, in terms of capacity, and in terms of reliability. Okay? So in the second bullet is reliability. Okay? And first one is capacity. And third, bullet number 3 and bullet number 4, these are performance. Okay? Okay, so let's conduct the capacity theoretical analysis for RAID number 0. So here, the different letters have different meanings. Let's assume N is the total number of disks. Okay, so this is N. C means the capacity of each disk. Okay, and in terms of performance, S is the sequential throughput. Okay, R is the random throughput, or the total number of I/O operations per second. Okay. Or IOPS. And whenever you're talking about storage performance, IOPS or I/O operations per second is the major operation, is the major metric, performance metric that is used to quantify the random throughput. Okay. And regarding performance, a third metric, the third letter. So we have another letter, which is D. Okay, so D is used to represent the random I/O latency. Latency for any single random I/O operations. Okay, so this is the latency. Okay, so let's first take a look at the capacity. So capacity is straightforward. It's N times C, because under RAID-0, it doesn't support redundancy. So that means we could effectively utilize each and every byte within this configuration to store unique data. It doesn't support redundancy. We can fully utilize each and every byte. So moving on to the failure, the reliability model. Again, because it supports zero level of redundancy, it supports zero level of reliability. The max number of disks that can fail under RAID-0 is 0. Okay? Reliability is 0. So moving on to performance to metric. Throughput. Recall that RAID-0 as a best case baseline for both performance and capacity is able to effectively aggregate the performance of each individual disk that are involved in this configuration. So in terms of sequential throughput and random throughput, it's just times the factor of n, right? If we're talking about sequential or random, times n, because we effectively combine a total number of n disks under RAID-0. So moving on to latency metric. So latency is the random small I/O latency for any single random I/O operations. It's D, right? Because here we only talk about like any one of these random I/Os. Its latency is D, because it just need to perform one single read or one single write. So it applies to both reads and writes. Okay, so this is RAID-0.